Chinese scientists just crossed a line that America's best labs, Google's billion-dollar quantum division, and 30 years of the world's most brilliant physicists have been racing to reach. And they did it with a method that might be simpler, cheaper, and easier to scale than anything the American team built. This is not a speed benchmark. This is not a press release. This is a peer-reviewed paper in one of the most respected physics journals on Earth, validated by a Western expert, describing a moment that changes the shape of the entire race. And the deeper you look at what actually happened, the more uncomfortable it gets for everyone who assumed America had this locked up. Let us start with the problem. Because most people have never heard of the fault tolerance threshold, and most people have no idea that it has been the central unsolved engineering nightmare of quantum computing since the 1990s. Here is what it means in plain language. Quantum computers use qubits instead of regular bits. Qubits are absurdly fragile. They collapse. They pick up noise from the environment. They make errors constantly. And here is the brutal part. The more qubits you add, the worse the problem gets. Scale up a quantum computer without solving errors first, and you do not get a more powerful machine. You get a more broken one. That is the wall. That is what has kept quantum computing from becoming a real weapon, a real tool, a real threat. For 30 years, the goal has been to build a system where adding more error correction actually makes the machine more reliable, not less, where errors shrink as the system grows. Scientists call that crossing the fault tolerance threshold. Cross it, and a scalable, practical quantum computer becomes theoretically possible. Fail to cross it, and you have an impressive laboratory toy. That is all. And for one full year, exactly one team on Earth had done it. Then China walked in. To understand why December 2025 mattered, you have to go back 12 months earlier to December 2024, when Google announced its Willow chip. Willow was a genuine breakthrough. 105 qubits. Published in Nature, one of the most prestigious scientific journals in the world. And for the first time ever, Google demonstrated quantum error correction operating below the fault tolerance threshold. That means as Google made its error-correcting code more complex, the error rate went down, not up. That is the behavior the entire field had been chasing since the 90s. Google achieved it first. The US tech press celebrated as expected. Every headline was a victory lap. Every article was a declaration that America was ahead, that Google had done something no one else had managed, that the quantum race had a clear leader. For one full year, that was true. And then December 2025 arrived. The University of Science and Technology of China, a state university in Hefei, a city most Americans could not locate on a map, published a paper in Physical Review Letters. The machine was called Zhuchongji 3.2, named after a Chinese mathematician who lived 1500 years ago, 107 superconducting qubits, distance 7 surface code quantum error correction, and an error suppression factor of 1.4. That number matters enormously. Anything above 1 means the system is operating below the fault tolerance threshold, meaning errors are shrinking as the code gets more complex, meaning the machine is doing the exact thing the field has been trying to prove possible for 3 decades. China's number was 1.4. The result was peer-reviewed. It was not announced on state television. The team published the mathematics for the entire global scientific community to check, and the checks came back confirmed. Joseph Emerson, an independent quantum computing expert at the University of Waterloo in Canada, publicly validated the significance of the result. This was not Chinese state media spin. This was physics. That is the second country in the world to cross the threshold, the first country outside the United States, and that alone would have been enough to make headlines everywhere. But here is what almost nobody covered. It is not just that China crossed the line. It is how they crossed it. Google's Willow processor achieves fault-tolerant error correction using a method that requires hardware-intensive DC pulse wiring. That means individual control lines running to individual qubits. It works. It is impressive engineering, but here is the problem with that approach. It does not scale. If you are eventually trying to build a quantum computer with millions of qubits, you cannot run a separate wire to each one. The physical infrastructure becomes impossible. The wiring alone becomes an engineering catastrophe. That is not a flaw in Willow exactly. Willow is an early prototype, not a final product. But it is the opening that China walked through. The USTC team used something completely different. They developed what they called an all-microwave leakage suppression architecture. Microwave signals can be multiplexed. Multiple signals, one wire. No need for the hardware-intensive DC pulse wiring Google relies on, and their approach reduced qubit leakage by a factor of 72 compared to standard methods, without the hardware overhead Google requires. Independent expert commentary described the microwave approach as potentially easing the hardest engineering barriers facing large-scale quantum computers. The conclusion from Interesting Engineering was blunt. The result shows that fault-tolerant quantum computers, with even millions of qubits, are possible in the future. Google won the first lap. China may have found the faster road for the marathon. Now, to be fair about this, because credibility matters more than clickbait, the scalability advantage of China's microwave approach is currently theoretical. It has not been demonstrated at millions of qubits. Nobody has. This is still very early-stage work. The race is real and both sides are far from the finish line, but the direction of the discovery is significant. China did not just copy Google's method and arrive a year later. They arrived a year later with a different architectural approach that independent experts say may be easier to build at scale. That is not catching up. That is potentially leapfrogging. And the error correction breakthrough was not even China's only quantum moment in 2025. Go back to March of that year. The same USTC team, the same machine in a different iteration, unveiled Zhuchangji 3 with 105 qubits. They completed a quantum random circuit sampling task approximately 1 million times faster than Google's Willow benchmark result, and roughly a quadrillion times faster than Frontier, the most powerful classical supercomputer in the world, for that specific task. Now, the honest caveat here is that the tasks were not perfectly identical in complexity, and Willow still has slightly higher individual qubit fidelity than the Chinese chip. Willow edges it at 99.86%, 2-qubit gate fidelity, compared to China's 99.62%. These are different machines making somewhat different trade-offs. The comparison is not a clean knockout, but the gap in raw speed on a shared benchmark class is enormous regardless of how you measure it. China is not just building fast, it is building reliable. Speed in March. Error correction in December. 2 major milestones in the same 12 months. This is not a country stumbling into quantum computing. This is a country running a coordinated program with a strategy and a deadline. That strategy is backed by money that makes the U.S. federal investment look like a pilot program. China has invested an estimated $15 billion in quantum computing research as of late 2024. That figure comes from Quareca market data cited by industry publications. The U.S. National Quantum Initiative, the federal program meant to coordinate America's quantum effort, invested approximately $5 billion, 3-to-1, and that is just the federal comparison. China's quantum firm count grew from 93 to 153 inches a single year. The government announced a 1 trillion renminbi state investment fund in March 2025, covering quantum, artificial intelligence, hydrogen energy, and other strategic sectors. China has already deployed a national-scale quantum key distribution network. 2,000 kilometers of fiber optic cable plus 2 satellites already being used to send quantum encrypted communications with Russia and South Africa. And in early 2025, BAQIS, the Beijing Academy of Quantum Information Sciences, set a world record by storing light information for over 4,000 seconds. A quantum memory breakthrough that barely made a headline outside specialist publications. This is not one lab. This is a country that built the road, the infrastructure, the commercial ecosystem, and the satellite network, while the United States was scrambling to reauthorize its own quantum initiative after letting it lapse. That part deserves a moment. The original U.S. National Quantum Initiative authorization expired in September 2023. The Reauthorization Act was not reintroduced to Congress until December 2024 and was formally introduced again in January 2026. The United States went more than a year without active authorization for its primary quantum coordination program. China did not stop for a single day. And the reauthorization bill that finally moved through Congress proposed new centers, new test beds, new workforce programs, extensions to 2034. All good things. All things that should have been moving faster. That is the part nobody in Washington wants to say out loud. But here is where this stops being a science story about qubits and become something much more personally uncomfortable for everyone watching this. The reason quantum computing matters to ordinary people is not the benchmarks. It is not the journal papers. It is the encryption. Every piece of digital security protecting your life, your money, your private messages, your medical records, your country's military secrets runs on mathematics. Specifically, it runs on math problems that are simply too hard for classical computers to solve in any reasonable amount of time. RSA encryption, the system protecting most of the internet, is based on the fact that factoring two enormous prime numbers takes classical computers billions of years. Quantum computers, once they are powerful enough, can solve that problem using an algorithm called Shor's algorithm in a fraction of the time. A theoretical quantum computer capable of running Shor's algorithm at scale could decrypt a key currently protecting sensitive government communications in under 8 hours. That is from a foreign affairs analysis published in June 2026. And China's own physicist Zhu Xiaobo estimated in March 2025 that universal fault-tolerant quantum computing of that kind is still approximately 15 years away. So, we have time, right? No, we do not. Because of 3 words: harvest now, decrypt later. The U.S.-China Economic and Security Review Commission told Congress in its November 2025 report that adversaries, including China, are already engaged in harvest now, decrypt later operations. That means collecting encrypted data today, right now, with the intent to decrypt it once quantum computers become powerful enough. The RAND Corporation noted in June 2025 that even if the transition to quantum-safe algorithms is completed before a fully capable quantum computer arrives, the massive amount of sensitive material that China and Russia have already harvested will probably be compromised. Foreign Affairs stated directly, China and Russia have already collected encrypted U.S. secrets, betting that some of the information will still be relevant once they have the tools to decrypt it. The U.S. government has mandated all federal agencies migrate to quantum-resistant encryption by 2035. Google accelerated its own internal deadline to 2029. NIST finalized the world's first post-quantum cryptography standards in 2024. The scramble is real, and the scramble is happening because the data pipeline is already open in one direction. The machine does not need to exist yet. The data just needs to be stored until it does. That is the haunting part of this story. It does not matter that the quantum apocalypse is 15 years away if everything stolen today becomes readable in 15 years. The clock is not starting when the machine arrives. The clock started when the first encrypted packet was intercepted and saved, and nobody knows exactly when that was. Now, to be clear about something important, no quantum computer today can break 2048-bit RSA encryption, not China's, not Google's, not anyone's. When researchers from Shanghai University in March 2025 used a D-wave quantum annealer to factor a 90-bit RSA integer, that was a meaningful proof of direction result. But 90-bit RSA is not real-world RSA. It is not even close. The practical breaking of modern encryption requires capabilities that do not exist yet and may not exist for a decade or more. Any video or article telling you that China can read your bank account right now is wrong. The threat is real. The timeline is not imminent. But the direction is no longer in doubt, and the harvest operation does not require waiting for the machine to be ready. The US has not been sitting still, and that matters for the full picture. Google's Willow still edges the Chinese chip in raw qubit fidelity. IBM's Starling roadmap is targeting 200 logical qubits by 2029. Microsoft's Majorana 1 chip uses topological qubits, a fundamentally different architectural approach that, if it works, could scale to millions of qubits with fewer errors than superconducting systems. It currently has 8 qubits and is extremely early stage, but it represents a genuine architectural bet. The NSF supported a team in 2025 that built the largest quantum bit array ever recorded, 6,100 neutral atom quantum bits. The Department of Energy committed $625 million to quantum research centers in November 2025. In May 2026, the Department of Commerce announced letters of intent with 9 companies covering $2 billion in CHIPS Act quantum incentives. The U.S. has the deepest concentration of top-tier quantum companies on the planet: Google, IBM, Microsoft, Quantinuum, IonQ, PsiQuantum, Amazon. That is a genuine strength. The US model is distributed across corporate research, academic institutions, and government programs, with diverse architectural approaches running in parallel. Diversification reduces the risk of betting on the wrong horse. That is smart. The problem is that distributed also means split, and it also means slower at reaching specific milestones when one country decides that one milestone matters most and concentrates everything behind it. And here is what makes the intelligence picture genuinely unsettling. The U.S.-China Economic and Security Review Commission stated in its 2025 report to Congress that the commission assumes China is aggressively pursuing cryptographically relevant quantum computing and deliberately obscuring where its most sophisticated programs are located and how far they have progressed. Read that again slowly. The official U.S. government body advising Congress on China said, "We assume they are hiding the most advanced parts of their program, and we do not know how far those parts have gone." The USTC papers, Zhuchongji, Zhuzhang, the published benchmarks, all of that is the civilian face of China's quantum program. These are academic teams publishing in open journals. The military programs that the Department of Defense flagged in its 2024 China Military Power Report, the ones aimed at quantum sensing for submarine detection, stealth vehicle tracking, GPS-denied navigation, those programs are not publishing in physical review letters. The visible progress is the civilian side. There is an invisible side, and the U.S. government is telling Congress it cannot fully see it. Only 2 Chinese quantum computing companies made the Quantum Insider's 2025 Global Top 80 list. That is not because China lacks competitive quantum companies. It is because most of the serious work is happening inside state-directed academic institutions and military-adjacent programs that do not show up in commercial rankings. The United States has never lost a major technology race to another nation in the modern era. It invented the transistor. It built the internet. It wrote the code that runs the world. The assumption that quantum would follow the same pattern was so deeply embedded in the American tech culture that questioning it felt almost unpatriotic. Google crossed the fault tolerance threshold in December 2024, and for 12 months, that felt like confirmation. America still had it. The assumption held. Then a university team in Hefei crossed the same line with a different method that independent experts say may scale more cleanly, and they did it 12 months later, and they published it openly in front of the entire world, and the checks came back confirmed. China's 5-year plan for 2026 through 2030 elevated quantum technology to a core future strategic industry alongside embodied AI, nuclear fusion, and brain-computer interfaces. The U.S. National Quantum Initiative authorization lapsed for over a year and was scrambled back into Congress while China was announcing satellite quantum networks and commercial deployments and world record memory benchmarks that barely registered in Western media. The real question is not whether China's scientists are talented. They obviously are, and Pan Jianwei's team at USTC has been at the frontier of quantum physics for years. The real question is structural. Is the American model of distributed, market-driven, multi-company, multi-architecture, quantum development fast enough to outrun a model that concentrates 3 times the state funding, picks specific milestones, and runs a coordinated national program with military backing and a deliberate strategy of not letting the world see its most advanced work? Because here is the thing about the fault tolerance threshold. It was not just a benchmark. It was not just another speed test or a qubit count record. It was the qualitative dividing line between a laboratory toy and a scalable machine. Crossing it is what makes everything else possible. It is the prerequisite. And for 1 year, America held it alone. Then China crossed it with a simpler method that might make the next step easier. The data is already being harvested. The machine is 15 years away on the optimistic estimate from China's own scientists. And America's migration to quantum-safe encryption is not due until 2035, which means the deadline is the quantum machine's arrival date, and the arrival date is the optimistic estimate, and the optimistic estimate comes from a team that just proved they are moving faster than anyone expected. The race that defines the next century of security, intelligence, military power, and economic leverage just got a lot less comfortable for the side that assumed it was winning. And the team that just changed the math is based at a university named after a river, working on a machine named after a man who lived a millennium and a half ago, publishing results that the entire world can read, while the programs nobody can see keep running in the background. Was America ever actually ahead, or did it just think it was?